So welcome to our webinar, our Spring into STEM webinar from UCL Engineering. More specifically, this is UCL Mechanical Engineering, and I'm here to introduce Dr. Lama Hamadeh, who's going to give this morning's exciting talk, a brief taster lecture, after which you'll have the chance to ask some questions. If you note in the bottom of the screen, there's a section marked Q&A, a button marked Q&A, and you can type your questions into that. And once the lecture is finished, the short lecture is finished, then Dr. Hamadeh will answer your questions. I may pose a few questions myself because it's exciting work. So you're in the session for machine learning as a potential tool for disease diagnosis. And giving the lecture, I'm pleased to introduce Dr. Lama Hamadeh, who is a relatively new lecturer at UCL Mechanical Engineering. She joined in 2021, and Dr. Hamadeh completed her PhD in theoretical and mathematical physics at the University of Nottingham in 2015, and joined the product design department at the School of Architecture. But now she's with us, and today she will be talking about machine learning as a potential tool for disease diagnosis. Seems there's no area that machine learning can't touch. So with no further ado, I will mute my video and my sound. If you want the best view of this, we would suggest in the top right-hand corner of your Zoom to click speaker view. And so you'll be able to see her expressions as she goes through, as well as the slides, giving you lots of rich and interesting information. So that's time for me to sit alongside you and listen to what she's got to say. And so over to you, Dr. Lama Hamadeh.
Thank you, Michael. I'll share my screen now. Can you see my screen?
Yes.
All right. So, hello, everyone. During this presentation, I will try to explain how the current blood diagnosis and testing procedure that is pretty much currently applied worldwide can be replaced by a high-performance computer with a machine learning algorithm and only one drop of only one image of dried blood droplet. So I believe most of you, if not all, have experienced the process of blood testing. So when you feel that you are under the weather, you call your GP, and after a couple of questions, your GP might ask for a blood test to make sure that everything is okay with your health. So, and you know that the blood testing usually is booked not at the same day of your GP appointment, is booked after a couple of days or after a couple of weeks sometimes. On the day of your blood test, after putting a rubber band around your upper arm to temporarily slow down the flow of blood and that causes your vein to swell, which makes it easier for the blood to be taken, a needle attached to a syringe is inserted in your vein and a sample of blood is taken. This sample of blood is taken to the lab where expensive machines are used to test this sample. The results usually takes a couple of days and sometimes a couple of weeks to come back from the lab to your GP. And at that time, you know whether you're healthy or you have a problem that needs to be treated. So you can see that the whole process is quite long, is quite slow. And at the step where your lab sample is where your blood sample is tested, and expensive machines and the size of a photocopier are used to do that. So our work here is asking the following question. What if we can replace all of this process by a high-performance computer with a machine learning algorithm where we can pass an image of your blood, a dried blood droplet, only one drop, and this machine learning can tell us whether you're healthy or you're not, you have a problem. Can we do that? Well, to answer this question, we need to go through a couple of steps. First step is, why dried? Why dry droplet? What's so special about dried droplet? Well, you know that evaporation and dry droplets is a very common phenomenon in nature. I think one of the most earlier works that studied the evaporation of liquids has been done in 1997 by Deegan. Deegan said that when a droplet is evaporated, it ends up with a pattern that has a ring-like structure, and he called it a coffee ring effect. And he said that all liquids, when they dry, they follow exactly the same final pattern of this ring-like structure, or a coffee ring effect. Actually, blood follows exactly the same process. At the end, the final pattern left by blood, it followed exactly the same coffee ring effect. However, blood is a complex biological fluid. It has a lot of components in it. It has red cells, white cells, platelets, plasma, chemicals. It has a it's a very complex biological fluid. So when it's dried, the final pattern is very rich. It holds a lot of information, and it could be linked to the health of the individual. Researchers have noticed that, and it has been a very expensive research on linking the final pattern left by blood to the health condition of the individual. And this is very important, especially for diagnostic medicine and forensic sciences. All of these researchers have followed the human visual observation. In other words, qualitative observation. So they said, all right, here we have, for example, 5 cracks. So this could be linked to this kind of disease, for example. Or the cracks here is like a spiral shape. So it could be linked to the other kind of disease. The color here is lighter than usual. So it's a visual observation. You can't find in the literature a research that has been analyzing this quantitatively. Now, what do we mean by quantitatively? Now, in general, quantitative research depends on analyzing data. So we need the data set. If we want to go through the quantitative path and we want to analyze the patterns of the images quantitatively, we need to build a data set. All right. So let's build our data set. Now, our data set consists of images taken from 30 male healthy volunteers. So we have 30 male healthy volunteers at rest, and from each one of them, we took 12 images of their blood. So in general, we have, or in total for this condition, we have roughly 360 images. Now, we made all of these volunteers to go through an extensive cycling exercise for like 20 or 22 minutes. Now, you might ask, why cycling exercise in specific? Well, it's well known that cycling exercise causes a lot of disturbance in the blood chemistry. So we made them go through the cycling exercise, and we did exactly the same thing. From each one of them, we took 12 images. Now, we did exactly the same after 2 minutes of the cycling exercise, after 4 minutes, and after 6 minutes. So each condition, so now we have 5 conditions. From each condition, we have nearly 360 images. So in total, we have 1,800 images. It's a relatively large data set. So our issue here is not the data set that we have, is how to make sense of this data set. So we have a large number of images. How do we use them? How do we organize them? How can we extract information from them? And here where machine learning comes to help. Now, before expressing or explaining what machine learning is, I think we need to understand the parent term or the broader term, which is artificial intelligence. So in very simple words, artificial intelligence describe applications that mimic the cognitive functions that humans interact with other humans' mind. In other words, learning, problem solving, decision making. The very first work that has been done in artificial intelligence was in 1950 by Alan Turing in his paper, Computing Machine Intelligence. He said, can we build an intelligent machine that can learn from experience? And then can we test this intelligence? So this is the parkour if you want to go and read about his first idea about artificial intelligence. Now, there are two subfields of artificial intelligence. One of them is machine learning. So machine learning are just algorithms that can analyze data, learn from it, and do or make decisions based on the learned insights. There are a lot of tasks that you can do with machine learning algorithms. So you can do clustering, you can do regression, you can do classification based on the problem you are solving. Now, there are second subfield of artificial intelligence, and some people might consider it a subfield of machine learning as well, which is deep learning. So deep learning is basically a multi-layered structure of algorithms. We call it neural networks. Now, artificial neural networks has this unique capabilities of solving problems that machine learning cannot solve. So now we know these three terms, most important terms in this artificial intelligence field. All right, let's go now to take the machine learning, choose the most appropriate algorithms, and let's apply it on our data set that we already built. All right, now the data set that we have is images of dried blood droplets. Droplets, or these images, have a lot of information. We have the color, we have the shape of cracks, we have the number of cracks, we have the chemistry of the blood. We have a lot of information. Each image is a multidimensional system. Multidimensional system means it has a lot of information. Do we really know which information that is most important for us for discrimination purposes or for classification purposes? No. So we need to extract these most important information. One method or one algorithm to use this is what we call a dimensionality reduction. Now, I'm not going to go into the math of this, but there is an analogy. I've heard it before, and I really like it because it really resembles the meaning of what dimensionality reduction is. Consider your data set is like a trash pile. Why trash pile? Because you don't know if it's useful or not. It has a lot of information there that you don't know which one to pick. And you would like an algorithm to extract this, to tell you whether this is important or not. And this is where dimensional reduction comes to place. Dimensionality reduction basically shines a light on your data and tells makes something coherent out of it. Illuminates the situation, makes you understand what are the most important features that you need to use in order to make sense out of your data. All right, so we applied dimensional reduction. One of the most common techniques of dimensional reduction is principal component analysis, or what we call it PCA. Okay, so we applied PCA on our data set. Now we need to discriminate between a pair of these conditions. So we have 5 conditions, if you remember. One algorithm that we can use is what we call it linear discriminant analysis. Very simple words. If you have 2 clusters, so for example, here you have the purple cluster and the blue clusters. This algorithm basically searches for the line that maximizes the separation between these 2 clusters. In other words, does this line maximizes the separation between these clusters? Well, you can find here that the distribution between both of them is really, really big overlap. There is big overlap between both of them. So we can say this is very poor projection, or there is poor discrimination between both of them. All right, what about this line? Well, this line, you can see that the overlap between these 2 clusters is very small. So we can find, or we can discriminate between these 2 clusters along this line. This is the aim of this algorithm, is to search for this specific line that enables us to discriminate or classify these 2 conditions. On a side note, these 2 algorithms, the PCA and the LDA, usually are applied together on data sets as machine learning algorithm. Okay, we applied now these two algorithms. Let's see if we end up with a reliable model, a good accuracy of our statistical model. Okay, so we try to apply this and discriminate between baseline and the peak, or the baseline and the cycling images. And we end up with an error rate of 11.6 here. 11.6 means that the accuracy rate that we have is nearly 89%. 89% is very good accuracy. We did exactly the same, and we compare between baseline and 4 minutes, and we end up with an error rate of 10%, which means that the accuracy rate, the accuracy of the model is 90%. Very, very nice. What about baseline and 2 minutes? Well, we end up with an error rate of 13.3. It's a bit higher, but still very good. Now, the surprise here was when we discriminate or classify baseline in 6 minutes, where we end up with an accuracy rate of 95%, which is amazing. So if you have two clusters, you can classify them very accurately to an accuracy rate of 95%. All right, now this is the machine learning algorithm. My fourth year mechanical engineering group decided to take this project further and to apply deep learning algorithm this time in a hope to beat the record of 95. Well, they actually did. They actually beat the 95, and they end up with 97% accuracy in discriminating between the baseline and the 6 minutes. All right. Now, so far, we have used a data set that contains 1,800 images of healthy, different conditions of healthy blood. Now, the aim or the question that we started this project is that, can we use this for discrimination between healthy and diseased? Now, this is what our future work, or the very first straightforward step for our future work. We need to build a new data set, but this time it has to be between healthy and disease, and apply exactly the same algorithms that we have, because there is a proof that our algorithm does work. And we can see that how the accuracy changes, what are the different diseases that we can use in order for this algorithm to really be a potential alternative to the currently blood testing process. And that's it. Thank you very much. Any questions? I'm happy to receive any questions about.
So we have one question in the Q&A, which is how do we use Daniel asking, how do we use mathematical principles for this?
What do you mean mathematical principles? Is it the algorithm that I mentioned, the principal component analysis, or in general?
I wonder if we can get it in general, he's saying.
In general, okay. So I think the one thing that I could mention is how to calculate the error rate, for example. The error rate of the statistical model. So basically, the error rate is calculated between to compare between the predicted and the ground truth. Every time this error is calculated, the parameters of the model is adjusted. This will be repeated millions of times, and each time the parameters of the model is adjusted. And in order for, at the end of these iterations, the error that we get is as small as possible. Another thing that I can come across is using matrices. When we use principal component analysis, we use matrices. And I don't know if you're familiar with diagonalization, correlation matrices. These are basic mathematical concepts that we use when we apply, for example, dimensionality reduction or the other algorithm. Yeah, I don't know if I answered your question.
Okay, we haven't had another response from. Oh, let's have a look in here. Yes, you did, says Daniel. Thank you.
Good.
Andrew's asking, do you think there are other applications of this model?
Other than the medical application, yes, there are. There are hundreds. You can apply it for weather prediction. You can apply it for financial trading. You can apply it in industry. Actually, deep learning can be applied in self-driving cars. Amazon Netflix uses deep learning a lot. What else? Alexa, Siri, the chatbots are prime candidates for using deep learning. So there are a lot of applications, automated applications that use machine learning and deep learning algorithms. Yes.
Well, based on saying that, I would. It's almost a silly question, although we say there are no such things. What's the appeal to you, particularly of machine learning? Why is this a field that you've chosen?
So I'll give a reason for this work in specific. So you can see that if you use machine learning in this, you can first scale down the size of the machines that we use. You can have a quicker response. So as you can see, the process that we have for the blood testing takes a lot of time and it's really, really slow. For using machine learning, it's only one click of a mouse and you can know if you are healthy or not. Also, it's cheaper. So, for example, here in the UK, mostly we don't pay for blood testing, but for other countries, for example, in the US, they pay a considerable amount of money for blood testing. For using machine learning, it's quite cheap as well. If you manage to get a high accurate model, you will be confident that your model is reliable and the results that you're getting is also reliable as well. So yeah, and I think machine learning has proven now in other applications that it really works. So that's what really interests me in machine learning and in this project in specific.
Okay, so we have a request for a suggestion. Thanks for the Timothy saying, thank you for the very interesting presentation. Could you suggest a book regarding Alan Turing?
Can I suggest a book? I can suggest the paper. I don't have a book on top of my mind, actually, but I can suggest the paper that I mentioned in the presentation. I'll go back to it now and just scan the barcode and have a read through this paper. It's really interesting. And it shows you how the very first idea of intelligent machines, how it came to Alan Turing's mind at that time, and how this evolution from 1950 until now makes this intelligent machines get improved and improved.
Okay, there is another question coming in. Is there adjustment for 2023? Do you mean adjustment in terms of expected grades, Daniel? You mean that? Okay. What I would say is that the demand for places at UCL Mechanical Engineering is so intense, record numbers of applications each year, and because of that, there is very little room for anything other than the required grades. Even with the required grades, it's still very competitive. So you have to make your absolutely best to meet the grade requirements as stated in the degree program. For the last 4 or 5 years, we haven't had any students other than special students from disadvantaged communities or just areas. We haven't had any space for adjusted grades on the program, I'm afraid. So yeah, ace those A levels is the tip if you want to come and join us. It's very competitive. Okay, so we're just about finished now. So my thanks to Dr. Lama Hamadeh for her really interesting presentation.
Thank you, Michael.
And we will see you at another Spring STEM session very soon. There is one
Yeah.
later on today and two tomorrow. On behalf of UCL Engineering, thank you for joining us, and thank you, Dr. Hamadeh, for your presentation.
Thank you, Michael, and thank you all for attending.
Take care. Bye-bye.